So this is a smart camera panel. We got I think 4 panelists, so this is the last official segment of the meeting. There's no one booked in this room afterwards, so as long as people want to stay afterwards, we'll stay and we can look at other things that people brought to show off, show and tell, or whatever. But I do want to complete the panel because we got people organized to present on smart cameras. So what we'll do is Tom, who's online, is going to lead off and give a market. Well, I'll start off with setting context. Tom's going to talk about a market overview and then the smart camera that he's familiar with. Then we'll roll to Ray, who has a demo of smart cameras. And then depending on where Doug is, Doug's having some technical issues at the moment, so he's going to carry on working on that while we go through the first couple of panelists. I've just got like a few words about the camera, the smart camera I've used, and then we'll plug in Doug whenever he gets ready, or at the end if he doesn't get it all working by then. And then so we're open to and encourage questions as each panel member goes through their presentation, and feel free to just chime in. We'll move the camera, the video camera around for the live demos, and then at the end we'll have open mic kind of like discussion with the panelists of what their experience has been like. And at the end, then we'll call, once the panel's done, then we'll say the official part of the meeting is over and we can do show and tell for whatever anyone brought. Okay? Right. So the panelists are Tom Crawford, who's in Ottawa, Canada. He did a great camera survey of all kinds of cameras that are on the market, and he also has experience with an ESP32 cam. Doug has a PiNSight that he's going to hopefully demo. I brought an OAK-D Lite. I don't have a demo. It's just a talk about what it was like and specs. And Ray has a demo with an MaixCam. So smart cameras, what we're really talking about here is vision with edge AI. Edge AI is a term that you run across as being referring to smart cameras and smart things that are at the edge of the internet that have AI built into them. So as a baseline, a Raspberry Pi with a camera is not with a dumb camera is not a smart camera. The robot host does the processing. That's not a focus of this panel. In some ways, it's interesting as a benchmark. So Bob Cook gave us some real-world data of the kind of performance he saw running AI on a Raspberry Pi with a dumb camera, but that's not a focus of this panel, except in as much as it expresses a baseline against which you might evaluate improvements. So what we're really looking at here is camera plus MCU. So for example, there are two main, as far as I can tell, two main divisions of the market. The camera with an MCU. An example is the ESP32 cam, which is a module that has a camera and an ESP32, and Tom will talk about that, which has low cost, modest performance. Then you have camera with a vision AI ASIC. Is sort of the high end of the market segment, as best I can tell. And Tom, if you want to pitch in on this and expand on that, please feel welcome. So, but examples of that would be the OAK-D Lite, the PiNSight, and the MaixCam. High cost, higher performance. And really what I wanted to get out of this panel, really for my own elucidation as much as anyone's, is the camera bias conundrum. Because there are so many smart cameras on the market, which is best? How should I trade off price versus performance? And what is each one best for? So with that, I'm going to ask Tom to take over and let's speak to the market summary and then go on to his experience with the ESP32 cam.
Sure. So I'll go through this page, and then Paul, I'll cue you for the next page, since I assume I can't control it.
I can step forward, or if you want to share, I can display what you're sharing on the screen here.
No, I'll when I'm ready for the next page from your presentation, I'll just let you know to move the page ahead.
Okay, and if you do want to share anything different beyond what's in the presentation, then let me know. We'll work it out.
Okay, I put together this spreadsheet after I'd started to build a low-end ESP32 cam machine learning cone detector, and was focused primarily on having done some performance research. I was focused on the low end of the marketplace and taking a look at moving past just using a microprocessor for the execution of the inference engine to starting to look at, you'll see it on the top line, called NPUs. Paul has referred to a class of them as vision ASICs, but they're often also known as neural processing units, or NPUs, and you'll also see them referred to as tensor processing units, which is optimized to execute the kind of machine learning model that comes out of the Google TensorFlow Lite training environment. So there's those two classes of as Paul calls them, ASICs, a production chip that happens to be optimized with highly parallel, very simple processing hardware to run the specific algorithms required to execute machine learning inference engines very, very, very fast. And I was very intrigued to find out that there are quite a number of them at very low cost. The top of my list here is simply the ESP32 cam. It's a relatively straightforward device. You're probably all familiar with it. Comes with a cam on it. I plug them into a USB interface, which I'll describe later. They run at 240 megahertz, but because they have a single precision floating point hardware, which runs hardware effectively at that same rate, they actually perform very, very well because of the hardware math mechanisms they have. They generally come with a 2 megapixel camera, and that's what I'm using. I'll talk some more about it later. When I started to look at some online reviews of entry-level object identifiers, I quickly ran into the Seed Grow Vision AI version 2. Really, really cheap, and it was the first one I looked at that combines an MCU with a neural processing unit. The neural processing unit is an Ethos U55. I've actually looked into that one quite a bit more, and later on, when the formal part of this is over, perhaps we can take a look at some additional performance information, comparative information, that compares it with a number of entry-level smart cam mechanisms. That turned out to be very, very interesting. It will probably be my next purchase because I'm quite impressed with them. The third entry, Arducam Pico 4ML. I put it on the list because initially I was quite intrigued that somebody would try to use a Pico to run machine learning. Arducam did it and sold this device for a few years. It's now discontinued, but there's still a lot of them on the market. I would not recommend it. There's no neural processing unit. The Raspberry Pi 2040 does not have floating point hardware. It doesn't run very fast. It's not a really good choice. So it's on the list just for reference sake because I ran into it. You can buy one if you want. They won't perform very well. So don't buy that one. The Seed MaixSense A010. I think one or two of you may have these. They're an impressive little gadget. They're not a full video camera, of course, They're a multiple array time of flight sensor with a display as part of the package. They're very, very impressive, and they're not very expensive. But I still think that if you can do full camera image processing, then you'll have somewhat better results. This closer to my screen. The CPI MaixCam Pro, I think we're going to have Ray talk about that some more. Is that correct, Ray?
Yeah, Ray's going to talk about the MaixCam Pro, right?
Well, I don't have the Pro. I have the one prior to that.
But the MaixCam.
But it's got the same.
Yeah, okay. I understand that the hardware is pretty much the same between the MaixCam and the MaixCam Pro.
Yeah.
Okay. The Pixie 2, I don't know whether anybody in this group has a Pixie 2. They seem to be an oddball. They do not have a processing unit for neural processing, and I'm not sure that you can even reprogram them beyond the half a dozen things they're designed to detect. Anybody know?
Yeah, as far as I know, you cannot. The Pixie 2 kind of featured, in addition to like blob detection, it could do line following. It could recognize intersections, and it could read simple barcodes. But that was it as far as
that was my impression as well. That essentially you could not implement your own cone detector.
No.
Okay. Next slide, please, Paul.
Slacking on
The DF Robot Husky lens has been around for a little bit. It has an early neural processing unit on board, the K210. It's not particularly powerful, but it does do quite a nice job, and I believe it can be reprogrammed on conventional machine learning frameworks, training frameworks. I don't think, given the price performance of it, it probably would not be my first choice. The company that makes the K210 has replaced it with what's called the K235, which is far more powerful, but is also new enough that you don't see it appearing in a lot of entry-level smart cameras yet. So I don't know that I would pick up a Husky lens unless it was really cheap. OpenMV4 cam. Some of you, I think, Pat, you mentioned you have an early version of the OpenMV4. Looks nice, but there's no special neural processing unit on board. It's just a very fast Cortex M7,
right,
with a big camera on it.
They do seem to have edge impulse support, and the more expensive OpenMV cameras are supposed to support it. The one that goes for, like I have just a plain H7, not the H7 Plus. That one, they said they felt really didn't have enough memory to be able to do, to load models of any significant size to be able to run it. So the more expensive versions, and I think he left, but Mike Williamson has one of those. Supposedly you can do, AI on it. It's got enough resources to.
Okay. So the next one designed to work with a Raspberry Pi. So Doug's going to talk about that, and I presume he has a more advanced AI hat as well. The OAK-D Lite, Paul, you're going to talk about that.
Yep.
The Arduino NicoleVision, I think at least one member of the club has one of those. Considering the price, I was quite surprised that it does not seem to be particularly powerful. And in fact, in performance comparisons, it is not very powerful. So it's probably not your first choice for looking at implementing machine learning. Nice stuff from Arduino. I mean, very good hardware, but not particularly powerful from my review of it. I stuck the last one in because it popped up in my searches. It starts to exceed my personal limits on how much I would spend, but this Jervois Pro is an astonishingly powerful box. I was really, really impressed with what it was capable of. You can see from the list here a lot of MCU power and a lot of NPU power as well, and it's got a huge amount of memory on board and a nice camera. That's it. So Any questions on the summary?
No, that's great.
So it's kind of my flavor of if I was going to go out and look for something to pick on next, what would I pick? So
Yeah, I thought this was a great table when I saw what Tom had produced as a survey of these are the things that are out there and how much they cost and what their performance specs are. I thought, wow, that's fabulous information if you're looking at buying a camera, a smart camera. Okay. Do you want me to move on to the next slide?
Next slide, please. Go ahead. So I thought before I went and talked about the ESP-CAM cone detector I built, I should probably first put it in context. I got interested in this last year when I started to work on my first outdoor autonomous robot, thinking, well, I'll just put a GPS on this thing and the GPS will get me close enough and I'll use an ultrasonic detector and a bumper switch and I'm golden. I'm all set. It doesn't work that way. I've learned a whole lot about GPS navigation, and I've also learned a whole lot about typical non-contact distance sensors, which have problems with object detection in cluttered environments. I actually put together an outdoor course for us to potentially use, Pat and myself and John at one point, and that's when it became clear that the outdoor environment was a lot messier to detect stuff in than an indoor environment. So simply using simple distance sensors was not going to help me get that, to cover that last 2-meter gap from where the GPS might leave me to trying to figure out where the cone is. So I started to look at implementing cone detectors. I'm a member of the Vancouver Robotics group as well, so I saw an early version of Bob Cook's presentation and listened to his discussions of how he was doing at building a cone detector for his outdoor robot, and that was fascinating. Part of my goal as a hobbyist is to be frugal, to use the things I have. You know, I'm well into retirement, and I've been technically inclined my entire life, and I've accumulated a massive amount of stuff, and I'm trying not to buy any more if I don't have to. So I want to use the stuff I've got, and I've got a bunch of ESP32 cams. I also like to not spend money if I don't have to. And I wanted to learn all about this machine learning stuff. I ran across DroneBot Workshop's article entitled ESP32 Cam Object Detection with Edge Impulse, which I highly recommend. There are several articles out there, if you search for them, that will explain to you how to use Edge Impulse. But Bill's approach towards producing these articles is extraordinarily good. And I simply followed his article with my ESP32 cam and my free Edge Impulse account and used it to program my cone detector and had no problems at all. And I'm really, really impressed with Edge Impulse.
And if I can interrupt for a second, Tom, just to say that if you look back on the some RBNV sessions from late last year, you're going to see Tom showing how to use Edge Impulse and the results that it gave.
Yes, I admit I came across in those presentations as being extremely enthusiastic about Edge Impulse, acknowledging it was the only environment I had ever used, but my God, it was easy. We'll see. I'm going to try some others this year. Next slide, please. So I'm not there in person, so I can't show you my device. So here's some pictures of it. The box on the left, I've simply packaged up my ESP32 cam inside of a 3D printed box so I could stick it somewhere on my robots. I'll try this out on a couple of robots. The picture on the top is simply an ESP32 microprocessor board with a cam on top of it, the standard unit that you can buy for $5 or $6. And the second printed circuit board underneath it is simply a USB interface. It has a USB chip and a connector and a voltage regulator and a couple of push buttons, and they're designed to mate together. And they're very small, relatively low powered, and they fit neatly inside of a 3D printed box. In the course of developing this prototype on my workbench, it became clear very rapidly that the debugging will go a whole lot easier if you can see what's going on. Hence, I added a display to this device. The initial display was a monochrome, about the same size, but just monochrome graphic. So it showed the text and it showed a few rectangles, but that still wasn't enough. So I switched it to this color graphics TFT display because I wanted to add the actual camera image which the inference engine was seeing at the time it was processing the data. And that turned out to be...
Yeah, trying to figure out how. Oh, got it.
Sorry?
Sorry, Tom, we had disruption here.
No worries. So that turned out to be extremely valuable to be able to see the actual image that the inference engine was processing at the time. These are relatively small images because that's how you make an ESP32 without any special processing hardware. That's how you make it actually run in a reasonable amount of time. The text on the left simply captures some of the relevant parameters associated with the object that was detected and with the execution progress of the code that's running. The white rectangle, the large white rectangle, shows the image that's actually being processed. These neural networks require square images. You have to have the same number of pixels horizontally as you do vertically. So I simply outlined that, even though the camera image itself is more rectangular than square. And I chose not to squash the image, but to simply crop it. This happens to be an actual image from my device I took a couple of days ago, which helps you see what the picture looks like and what the actual detection mechanism looks like. Now, let's go on to the next slide, please. I may come back to this one, but go to the next slide, please, Paul. So just covering off some of the items that Paul thought would be useful. The physical box, 200 milliamps at 5 volts. That's measured on the USB connection. The board is very small. The overall case, 1.5 by 2 inches by 1.25. And of course, the electronics inside are smaller. The box is perhaps a little bigger than it needs to be. I'm not a mechanical engineer. I'm not a package designer. And I honestly hate doing that kind of work. But I also can't leave all the parts hanging out in the wind. So it's not a bad little box. It serves its purpose. The electronics are somewhat smaller. The camera is interesting. The standard camera that used to come with an ESP32 is an OV-2640, a 2-megapixel camera. Fixed focus, very simple optics. But that particular camera contains a hardware JPEG converter. So embedded within the controller that's inside the camera, you can ask it to give you a JPEG, which means the transfer time over the DVP interface is very fast. The latest 2 ESP32 cams that I bought do not have that camera. They have an equivalent size one, a 2-megapixel camera, but it no longer has the JPEG conversion mechanism built into the camera controller, which would be a problem if you continue to use Edge Impulse, because Edge Impulse requires a JPEG formatted image in its current implementation, its default implementation. So for those of you who may choose to mimic this, check carefully which camera module came with your ESP32. Because if it doesn't do hardware JPEG, then you'll have to write some code to provide some conversions. And that would be tedious. It's doable, but it's tedious. So be aware of that. The interface by default is a USB serial interface. I'm adding an I2C interface simply because I like I2C and because both my robot controller board and the cone detector board are I/O limited. I have very, very few pins left, so I'm trying to conserve them. And I like I2C interfaces. The TFT display uses SPI, which means it burns up 5 pins. And there aren't a lot of pins left after you hook a camera up to one of these things. The onboard processing. I mentioned before that an ESP32, this one is an ESP32S, which is one of the earlier dual-core ESP32s, runs at 240 megahertz, but has hardware floating point. And that means that the execution time of the math is very, very fast. And that is very much in favor of making this thing actually usable. I mentioned before, if you used a Pico, for example, Picos do not have hardware floating point, so their math processing can be slower. There's a reasonable amount of memory on board these ESP32s, not enough to run full machine learning inference engines. So I run a simpler version as required by Edge Impulse, which is called a, where is it here? It's called a FOMO version of a standard neural network algorithm called MobileNet, because there simply isn't enough memory to hold both the model and the inference engine code on an ESP32. So you have to use a simpler version, and that in Edge Impulse's approach, that's a FOMO version. The camera is has about a 45-degree field of view for the image that the inference engine is processing. That's a little bit small, and it gets even more interesting because the FOMO algorithm tends to introduce a coarser resolution on the information that it's processing. So it works with pixel clusters that are 7 pixels by 7 pixels. They're actually 1/8 of the full width of the camera image that we're working with. Okay. We've lost the slide, Paul. And we've lost sound. Can anybody hear me?
I can hear you, Tom.
Okay. I can see Doug talking, but I don't know what he's saying. I can only see him. Paul, are you there? We've lost the slideshow.
Hey, Tom.
Can you
got some
hear me, Tom?
technical- We're getting it fixed.
Yes, I can.
Okay, our laptop that we were using to record the session ran out of juice and died and got disconnected. So we're trying to recover. So just give us a minute.
Okay.
Okay, I'm going to put my mic back on mute and go back to the presentation sharing, and Mark setting the replacement up.
Okay, are we back in business? Are we there?
Nice to meet you, Nadine. Good luck hooking stick in here.
Thank you.
Show these old guys.
Do I need
I
need to mute yours? Oh, put your speaker.
Yes. Hey, thanks for coming, Ron, and thanks for being election administrator.
All right. Can you hear us, Tom? Okay.
Yep, I'm here.
Cool.
Okay,
All right,
we're back on.
online.
Okay. So the point I was making is, as I've gained experience with the use of Edge Impulse on an ESP32, you begin to run into some of the limitations of this approach with an ESP32, and that is that there's a significant amount of granularity in the ability of the inference engine to detect where the cone is with high resolution. FOMO models only produce the centroid of the object it found, and that centroid is dictated by the granularity of the FOMO implementation. which the default is you basically take the pixel size of the image and you divide it by 8, and that's the granularity of what it's going to process. There are ways to change that. I switched it from a granularity of 8 to a granularity of 4, and when I did that, then the model ran with less accuracy and it ran much slower. So I put it back to the way it was. One of the reasons for wanting to consider moving on to more powerful machine learning inference processors, but what I did build tends to work quite well for my purposes, so that's pretty good. Let's see, I use Edge Impulse, I use a FOMO version of the MobileNet machine learning neural network. I'm implementing a 60 by 60 pixel image for processing purposes. The Edge Impulse allows you to pick whatever you want, and I tried 80 by 80 and 96 by 96, but the performance was too slow. You can also pick monochrome versus RGB, and I chose RGB because monochrome accuracy is not nearly as good as using full color. The algorithm allows you to use an inference engine that will run in RGB floating point or in quantized 8-bit values. The quantized 8-bit values run just as well as floating point, but run much faster. So my models are quantized to 8 bits. I trained my model with 386 images. These are the images from Bob Cook's cone set. The Edge Impulse model produces C++ source code, which I then download into an Arduino development environment. I add a whole lot of code to what's produced by the Edge Impulse system in order to be able to add a bunch of diagnostics and add all of the color graphics display, the image processing that I display, and a bunch of other stuff. Overall, I'm getting about 500 milliseconds per loop, so 2 frames per second is about what I'm getting. And I'm getting accuracies that are quite high in testing. They're about 93% in testing. I find that my real-world performance in my workshop, can I just go back one slide, please, Paul? Backwards one slide. You can see the picture in the bottom right is simply the picture of the cone sitting in my workshop at the end of the desk. There's nothing special about the lighting. It's actually relatively low lighting here, but I get very high accuracies and I get quite consistent results. I have not taken this unit outside to test. I've only tested it in a couple of different rooms in my basement. It was minus 10 degrees C this morning when I got up. I'm not going outside with electronics in this weather. It can stay inside. The text on the left, X and Y, are simply the centroid locations of the cone that was detected. W and H are interesting because when you look at the picture, it looks like the inference engine has identified a bounding box or an attempt at a bounding box on the cone. In fact, all it's showing you is how many of the little quantized cells it used when it detected a cone. In this case, because we have 7 by 14, the 14 is 7 by 2, that says that it used 2 of its quantized cells in order to identify that there was a cone here. I typically see 7 by 7, but it depends how close you are to the cone. I'm using cones like this. These are simple 12-inch cones from the dollar store. I should point out at this point that I plan to use this for 6CAN as well. So there's my simple 6CAN. It's not really the same orange color, but it turns out that my cone detector does not a bad job at detecting these already. And what's even more interesting is the FOMO algorithm I'm using specializes in being able to identify multiple objects in the field of view simultaneously. And I can, in my initial playing around this week, I can already see that that's going to work very, very well from a 6CAN point of view. The system does an excellent job of identifying more than one can and telling you where each of them are, all in the same frame analysis. I like that a lot. There's not much else here. The second line from the bottom is simply the loop time, 500 and something milliseconds, and the bottom line, the camera I'm using has a built-in light sensing algorithm, which is part of its auto exposure control. And you can extract that information out and use it to get a feeling for the light level. The camera's auto exposure control is known to have some problems, so I've been experimenting with my own light controls using that input. That's not working though. That's about it. It's dirt cheap, about $8 US to put one of these things together. It works quite well for its intended purpose, which is to identify whether there's a cone in the field of view and where the cone is within that critical range between getting to the presumed GPS location of the cone and getting to where the cone really is. So in that sense, I find that it's working very well for me. I am interested, though, in moving on to better systems that will allow me to use a full machine learning neural network training algorithm, which will give me much finer resolution and will also give me a first estimate at depth, that is, how far away is the cone. I can't get that from the system I have now in any meaningful form. So a couple of improvement opportunities, hence I started to do the research in terms of what would be next. Later on in the discussion group, we can talk some more about what I think might be a good next choice. Any questions at this point? I don't think I have another slide, do I, Paul?
No.
No, okay.
Okay, well, thank you, Tom. Really interesting overview table and interesting results on the SP32 camera.
Like a small side question. So, like, what's the difference between like using, of course, something like the SP32 cam and just like hooking up like a webcam to like a computer and then spelling something like CB?
I can't hear the questioner.
The question is, what's the difference between using something like an ESP32 cam and hooking up a regular cam to a Raspberry Pi and running something on the Raspberry Pi?
And that's always an excellent question. Just as a backgrounder, I was curious about that myself, so I took my existing model and I told Edge Impulse to program it for a Raspberry Pi 4. When you do that, the inference loop runs in 3 milliseconds.
Versus 500 milliseconds, right?
500 milliseconds, yeah. Now, but what's really important is that if I were to do that, I would then be able to run full-blown neural network training algorithms, and I would be able to use bigger images in the training and in the observation. And I have not started very far down that path yet. But that's the next stage, is to look at how to produce higher resolution, get bounding box information, and basically do a better job of finding the cone and figuring out exactly where it is.
And the ESP32 cam only runs at around like 10 frames per second, is that correct?
2 frames per second is what Tom measured.
Yes, that's right. With my exact implementation. So.
Yeah, and it's perhaps worth pointing out that it's very difficult to compare apples to apples in this space, but Bob Cook, who gave us a talk in June, reported on using now it wasn't Edge Impulse, he had some different AI implementation, but it was running, as you said, on a camera hooked up to a Raspberry Pi. He was seeing about 1.3 seconds per inference, but he was inputting about 400 by 400 pixels, whereas what Tom reported as taking 3 milliseconds was analyzing only
96
pixels by 60
96
pixels.
by 96 in that case.
Oh, 96 by 96. So you're talking about 16 times the amount of pixels that Bob Cook reported on, and it was taking a second. So, you know, it seems that the number of pixels matters a lot, but the Raspberry Pi brings a lot more horsepower than an ESP32 is what I take away from that.
Oh yeah, oh yeah. Now, part of Bob's conclusion was even 400 by 400 pixels is more than you need, but I can affirm that 60 by 60 is less than you need.
Okay. That's good data. Thanks, Tom. Okay, anything else for Tom?
Yeah, so Tom, at this point, what would you recommend a new roboticist look at?
Okay, the short answer is go out and buy a Grove Vision AI version 2.
Well, I'll tell you what, why don't we defer that question because we've got other presenters who each have good smart cameras to talk about, and then we'll have a meaningful, I think your question is right on the money. But
Let's come back to it at the end.
Yeah.
Okay.
I'll have some more to say about it.
Well, just because you're next in the slide set, do you want to go next, Doug? Are you ready? Or
Yeah, I guess I can. I gotta get close. Let's see.
okay, so we can bring the laptop and the
Well, I think we'll try on the camera, but we'll see.
Oh, okay.
So I'm going to talk about the Arducam PiNSight, I guess. How would you say it?
Yeah.
PiNSight. And okay, physically, it's about the 88.5 by 58 is roughly the size of a Raspberry Pi length and width. And this camera is unique in that it is really a base, a Raspberry Pi base, which is the opposite of a hat. The hat goes on top of a Raspberry Pi. The base goes on the bottom. So this is meant to be mounted on the bottom of a Raspberry Pi. Okay, so that's a little different. It's 5 volts and 5 watts, so it takes about an amp. What that means practically is that you should have it plugged into one of the SUV3s ports on the Raspberry Pi. The camera is a 12.3 megapixel sensor. It has several different video modes, and it also has several output formats. But in use, you don't really worry about those things. You know, you just plug it in. So I guess more importantly is that it's got a fairly decent autofocus lens. It's an f1.8 lens, which is when I was doing cameras back in the day, that was pretty good. And it has 81 diagonal field of view, a 69-degree horizontal view, and a 55-degree vertical. So the one that we typically use is the 69-degree horizontal. So that means that when this camera is looking out onto the field, it's the 69 degrees of the horizon, which is pretty good. Default focus is 5 centimeters, which
2 inches.
2 inches, okay. 2 inches to infinity. And if you're 2 inches from your cone, you're probably up there. All right. Now, the interface, like I said, because of the power, is probably USB 3, and also the speed. Onboard processing, this is essentially the same thing as a neural compute stick too. It's really, and when Paul talks about the OAK-D Lite, this is essentially an OAK-D Lite. Okay. Otherwise, it is the same, roughly the same camera, but there's no depth camera on this machine. And what that means to you is it's cheaper. And I found personally that I had not developed the expertise to use the depth information intelligently, so this was fine for me. I decided to do depth or distance by a forward-looking TOF LiDAR. Now, it's a 4-tops performance camera, and it's about 27 to 30, closer to 27 frames per second. It's 416 by 460 pixels, and I have used 2 models on it. I've used a RoboFlow version 3 object detection fast. I don't name these things, guys. That's just what it is. And I've also used the YOLO version 11S. Now, in hindsight, that might not have, I found the performance to be about the same, but after more learning on my own part, I probably should have went with YOLO version 8. Okay, but that's different situation. Now,
tolerate less perform or more speed, less performance.
Probably, I'm not sure. Would have to see it. But what I found was just using the standard RoboFlow model that they give you, which I think is probably based on a mobile net.
Yeah.
Probably. That it's pretty good. I didn't have it. I'm not sure if I'd struggle too much more on that. You know what I mean?
Yeah.
That's definitely the easiest path to go. Let's see. Okay, now, like I said, I use RoboFlow. The reason for that is because what is it? Linux, the people who make the OD.
Oh,
Electronis suggested that. And I started this process off using the OD. All right. And you say, well, Doug, why did you buy the PiNSight if you already had an OD? And because you could do the same thing. There's no reason. Otherwise, if you already have an OD, you're fine. You know what I mean? But if you didn't have an OD and you wanted to save $50, then this is a possibility. Okay. So in fact, I'm using the same Python scripts that I used on OAK-D Lite on this camera. No difference. I just plug a different camera in. So, like I say, here's a chance to cheap out on an OAK-D Lite and get just the AI part and not the depth camera part. So that's it. Now, I think what I would like to do is see if.
So I'll need to unpresent, and then you're going to present off your phone, right?
I'm going to try. And you guys are going to out there in Canada are going to have to tell me if this works. Okay, so I should be able to hit. Okay, does anybody know how you do that?
What are you trying to do, Doug?
I want to share
your screen and share your camera.
Oh, wait a minute. Let me try this. Okay, I'm going to a full screen mode. So I guess that's equivalent to a pin.
Mm-hmm.
Can you guys pin me?
Yep.
Pin.
I got it.
Pin. Well, you got a full screen on now?
Oh, there we go.
Okay,
Yeah,
let's
sure.
try it.
Oh, good job, Mark.
All right. Okay.
You want to turn on your microphone on that, Doug? Unmute yourself.
Okay.
Because then they'll hear you.
Can you? All right. I don't want to get us doing sounds like a ringing. Huh?
You're good. Go ahead.
Okay. So
Shall I take this over to there and
how do I change the
get them, or maybe?
All right. So
Okay.
this is an OAK-D Lite, a PiNSight right here, and you can see that there's a Raspberry Pi mounted right on to the back of it. Okay. Now, down here.
Do we want people to gather around, Doug, so they can see better?
Okay. No, I'm trying to. See, they're
Okay.
having a little trouble, but it's picking up Ray's cone that he's got in the back there.
Oh,
See it? If I put a cone in a little closer field, like this, should pick it up right. I don't have any issue. Okay. Eric, can I ask you to be volunteer here?
The official
Okay.
phone holder.
All right, so I want you to hold that. Now, one of the things you want is discrimination. And so I wanted to be able to see a cone, but something that is orange, not to pick it up. So here you can, well, okay, so there's that. Okay, you can see it did pick it up there when I moved it real quick, but when it stands out and stabilizes out, it rejects the, well, come on now. And it's not rejecting it.
Demo mode for sure.
Oh, no. Well, you can see it doesn't like the cone, excuse me, the can as much as it likes the cone. Bring the cone in. It really likes the cone. Okay. And, you know, it is, but we would never have this in a contest.
That's right. Yes,
You could, you know, you can bring in a second cone here. I can figure out how to do it. And it picks it up pretty easily without any trouble. Now, here's something that I haven't done at home, but I noticed that it have, Dave, can we have your orange bag? That's what okay. So we're going to try and see if it'll pick up this orange bag. Trapped behind the table.
What do you want a bigger size cell?
No, what I'm trying to do is, it should reject
That shape.
an
orange bag.
it should reject an orange bag. And you can see it's, you know, you get a flash now and then, so, but it doesn't stay consistent. So how you would want to do that is in your filtering, you would say, you know, if I don't see the cone 6 times in a row or something like that. Okay, that's it. So it's got pretty good rejection. And you can see every once in a while it'll pick up that second cone in the back. The problem is I get into view here and it screws it up. See it?
Yep.
So there's still work to be done, but it's pretty effective at picking up cones. And I like that. And when it does pick them up, it usually does it with very good confidence. Okay, so that's pretty much my tale on the PiNSight. If there's any questions, I might be able to answer them.
Yeah.
Tom's got a question.
Oh, wait, I'm
Doug.
sorry. Yeah, real quick. Sorry.
Doug, in your testing,
Okay, start again, Tom. Sorry.
sorry,
We had you on mute.
Start again.
Mute it now. Sorry.
Doug, in your testing, how close in and how far away can you reliably detect a cone? Reliably meaning you're going to see it 9 times out of 10, for example.
There's still occasional glitches where I see it not pick it up consistently. It does do a little better outdoors. It does, but you know, Ray's cone is, you got 2 cones set up over there. Here's where the camera is. And I was picking, I don't know if you can see it, but it's picking up both of them right at the moment.
So how far away is that?
The first cone is probably 12 to 15. The
Okay,
second
good.
is probably 20 feet.
Or more.
Yeah.
That's another reason why I want to use larger images and a full-blown machine learning, because right now my reliable range maximum is only about 7 feet, which I think is pretty good, and it's good enough, but I was surprised it wasn't farther away than that.
Yeah. Yeah, I've seen these pick things. I'll be quite honest, Tom. I've seen them outdoors. I've seen it pick up a cone like at 40 feet.
Okay.
Okay.
And you're using 400 by 400 pixels?
Yeah, I believe so.
That's interesting because one of Bob Cook's comments was he thought 400 by 400 was too much.
Yeah.
And he was talking about how he thought he should go down in the number of pixels that he was looking at.
Or get an NPU.
Yeah, right.
Yeah.
Well, this thing has an NPUs.
Yes.
Cool.
Okay.
Well,
so-
thanks, Doug. Any other questions?
Any other questions? So, well, I guess my bottom line on this will be the camera I'm probably using next contest. I think it's a reasonable camera for $100, but this market is changing so fast. I'm going to show. Do you want me to show this other thing? It's off schedule.
You know what? It's almost 2, and
Okay.
Ray's still got a demo to do, and so let's keep moving.
So one more question, Doug.
You have a Raspberry Pi AI hat running right here in the room.
So we could do that after
$70.
in the show and tell. Tom had one more question for you, Doug.
What?
Now, my understanding is the PiNSight is not standalone, that it actually uses the Raspberry Pi for some of its processing. Is that correct?
Don't think so. Well, I mean,
So you can run it. So you can run it without the Raspberry Pi.
huh?
So you can run it without the Raspberry Pi.
If you had probably a version of the AI, what is the name of the DougP AI? That's the API that the OAK-D and everybody uses. Okay, because this camera, what you do is it has the model run, then it gets converted into OpenVINO format. All right, and so it's running that. Okay.
Let me answer, Tom. So I think the answer really is you can use anything that has the drivers and runs Luxonas's DPRG AI software,
Right.
and of which examples are a Raspberry Pi or a Linux laptop,
Okay.
probably a Windows laptop,
Yeah.
maybe I don't know about
I don't know if they have
Jetson.
Windows.
So you need substantial computing
do.
power in order to process the signal from the PiNSight.
Well, no. What you need the external computer to do primarily is to load the processing pipeline definition into the ASIC,
Okay.
and so after that, there's a very much lighter weight role for the main computer, be it a PC or a Raspberry Pi or whatever, that the camera is talking to, because the camera is doing all the inferencing or depth manipulation, stereoscopic filter, whatever.
Oh, yeah.
And it's just shipping stuff back to the host, and that stuff could be as little as ranges to areas of interest, or
Okay.
as much as
Okay.
complete camera images.
Okay.
It's very flexible.
Okay. Thank you.
Yeah, and like I say, I'll be quite honest, I basically used what was recommended from RoboFlow, and it worked. I didn't have too much trouble with it. I know on a Raspberry Pi, it can run on a Raspberry Pi Zero. So I don't know if that answers part of your question.
It does. Yes. Thank you.
Okay, so you don't need a 5 to do it. The thing is, what am I going to use my 5s for? But I know, I'll just put it on there.
Give me one.
What I'm just saying is I actually thought about doing that, about putting it on a Raspberry Pi Zero, but then you have to worry about, well, where are you going to get USB power from? Because the Zero doesn't, you have to add the
You have to have a
interface.
powered hub or something.
Yeah, so it just, it works. Don't mess with it. That's
Cool.
that one.
Well, thanks, Doug.
Yeah.
Good.
Any other questions, discussion on Doug's PiNSight? If not, we'll roll over to Ray, and I can bring the camera and laptop over to you, Ray. Doug, do you want to leave the meeting? Kick you out?
Okay, wait a minute. No. Yeah, go ahead, kick me out, because I don't know how to. Okay, I'm out.
No.
Okay, cool. Well, I still see something.
Remove from the call. Remove. Boop, there you go.
Okay.
Kick you out.
Yeah.
Enough guide power?
Hmm?
Enough guide power to?
Maybe an hour's worth, but that will fill pretty quick. But yeah, you can try it.
Okay.
Thank you.
Oh, man, it's kind of far away.
What's the one?
Yeah. If you're going to show, I'm not.
I can hold the laptop if you want.
I can hold the,
Cameraman.
yeah, I can hold the laptop. You go.
Okay.
I got it.
Move over 2 chairs.
Okay, there we are. You ready? There was a couple things that I wanted to show, but I think I'm just going to do a 10-second one on that one. This was a kind of my attempt to do like an omni lens, or a lens that would see 360 degrees. So right now, and it is reversed image. That's always kind of hard to deal with. But there's signature 1. That's that cone. And, you know, no matter where you move it in the field of view, if the lighting is good and my other stuff is good, it'll track around the whole thing. So it'll find it no matter where it is. Thing is, it does make the images very small. So usually I'd use those larger, I don't know, they're like craft cards that are, you know, brightly colored. I get like a fluorescent orange one and hang it on a basically a post so that I could see it like from 10 feet away. So these are considerably smaller. So
Do you have an image on that screen, because it's not coming through on the camera image?
oh, it isn't. Do I have an image on it? Oh, you mean like a still?
Just the picture.
Yeah.
Oh.
You're fine. Fine with it.
Oh, that's good. You can see it now.
And you can see it.
Okay. Yeah, it's kind of dark.
Oh, yeah. Now I see it.
Yeah. Okay, so that was one thing. A lot of people had interest in that, but that's not the star of the show. So we'll move on to that.
Actually works pretty good.
Yeah, it's pretty good. The it's like a conical, rounded conical shape. It's more, you know, conical on the sides. It doesn't come to a sharp point. It comes to like a rounded point. And it was actually, there was an LED that, you know, this is like a lantern type flashlight that sat in the middle of this and shined up and broadcast the light around. So like the old lanterns used to. Anyway, so I am going to get rid of that. And this is actually.
So that's just a mirror on the top of the camera?
It's like a,
It's like a.
Flashlight mirror, isn't it?
Yeah.
Yeah, a reflector basically.
Yeah, you look.
Anyway, okay, where is
You can
that?
slide under there if you like to.
Okay.
You can look up at it. See?
Oh, yeah.
Yeah. So it's actually the camera lens is facing up right in the center. I have this on it because it's, you know, if there's any extraneous light, it kind of
Fix it up.
can wash things out. So, yeah. Anyway, on this one, this is the MaixCam, and basically, it's camera, processor. It's got a touch screen on the back, and one of the things I have to do is find the backup client. Okay, that should be running that. Oops.
There it goes.
Yeah. Okay. Okay. Find code. It's going to give me a barcode that I have to read. I should have done that first, but oh well. I think I can still do it. And basically, to create the model, you can collect the the images on the phone. That's not what I want to do. Let's see.
When you say on the phone, you mean on the camera?
Yeah, sorry, on the camera. That's to deploy the model, and then there's one other choice, but I don't want to do. Oops, yes, that one. Okay. There we go. Okay, so it's going to load the model now for the stuff that I've done, and that's it's like almost 6 megabytes of data that's going to load for the model.
Oh, that's interesting. So on the PC, it shows a barcode that tells the camera where to go and find the model.
Yeah, yeah.
Oh.
You don't have to do that on every power up, do you?
No, you can actually put it in, permanently in there. Okay, it's almost loaded. Anyway, the model that I did was not a very good model. I had 60 images total, and I think 10 of them were of just background. And usually, you'd like around 300 pictures or so. So what I found is, and I actually did it with that cone, and it's very picky. It doesn't work when it shows that cone, or when I show it that cone. And this is going to be a little difficult here. So if I can do this. Maybe I brought some black tape to tape it in there. Anyway, so if I show it that cone, you can see that it's actually calling out the cone and it's highlighting the border. Can you see it?
Mm-hmm.
Okay.
Oh, wait a minute. No, I don't see it.
Where'd you put it there? Okay, let me see. Right there. Can you see it now? Yeah, this is probably the worst way to do this. I had it so you could see it on the screen, but like 2 days ago, I tried to update it. Yeah, so when it fills the image, it finds the cone. When I go, and it does it a little bit to the left, and it does it a little bit to the right, just as long as the cone's in there. Actually, it's detecting that cone much better than it used to, because the other cone it's not quite twice as tall, but it's taller, and that's the cone that I trained on. And so it's kind of like what Doug said. You don't really want false images or false recognition. But the demo mode has. Yeah, I should have put that on there. Anyway, let's see here. Okay, and so fire extinguisher, it doesn't really catch the fire extinguisher. Doesn't think it's a cone. I hook a can up to it. It's kind of indicating that's a cone. A little bit there. I have to kind of tilt it back to make it do it, but because I think the cone is more pointy than a can is. So it is doing it. Okay, right now it's taking like 320 milliamps, so a lot less than any combination Raspberry Pi or other camera would take. Let's see, I can stick in front of it. So it's kind of rejecting that, not finding cone in that. But again, when it gets to about the full size, it thinks it's a cone.
That's probably your training set.
Yeah, and like I said, I only took 50 pictures and 10 background.
Yeah, and probably, so to a point, this is the reason why I think a training set should have alternate colored cones, because if it always finds a cone is orange, then it will, it kind of loses its coneness detection. It becomes more keyed on the color. So you want.
That's weird. It's not finding the cone at all.
Yeah.
Seems to like this one today.
Okay.
But as far as lighting, that may be, the color of that one may be closer to what it is. Yeah, it's picking it up pretty good. Over there, with like a confidence, that's 7.7 roughly, a little under. Thinks it's a cone.
Yeah, it's the darker color.
Yeah. So it's very cheap. I think $54 including shipping. You can put different lenses on it. You can do pretty much everything as far as what an OpenMV-H7 can do, like kind of the classical image processing stuff. Like if I get out of this.
And does this have a vision processing ASIC, or is it all in a CPU?
It's the information about that's kind of vague. They said it had two processors, one that ran at gigahertz, another one that ran at like 700 megahertz. Tom had it in his chart.
Maybe we'll go back and have a look at Tom's chart here
Yeah.
a little bit.
It does have an accelerator in the camera.
Oh, it does.
Yes.
Okay, thanks.
And,
That's what I was saying.
My note says it has 2 RISC-Vs and 1 ARM A53. There's no mention of any ASIC.
Yeah, but I thought it was optional for the ARM core. Doesn't it say that? So it could have or it could have 2 of the whatever that C906.
They're 32-bit RISC-V processors.
Yep. Okay, so I just wanted to show this real quick. There it goes. Okay, this is Max Vision.
It's all dark.
Yeah.
Very dark.
Very dark.
Can't see anything.
Oh, darn. Yeah, I guess my office is a lot darker than.
Brightness control on the screen on the monitor.
There is a
It's a
setting.
isn't there a button? Go ahead, let's see. Yeah, over there. The
Okay.
FN and then the
Okay.
plus.
Oh, yeah.
Okay, there is a way to display white text.
Okay, your screen is I can't see nothing.
Let's see, appearance. That one. Oh, color mode, dark, light. Can you see that?
Better.
Okay. Good. Let's use that. Okay, so let's see. I'm going to try to connect to it.
Does it make sense for you to join the call?
Oh, and
Is that
bring this all over there or something? Or,
present on? Or that
it could. Can you see that? Is it showing up?
Not really.
Oh, not really.
Not
Okay,
great.
yeah. Okay. Yeah, we could do that.
bring up a browser, go to DPRG, and hit the quick load or quick join.
Oh, okay. All right. Just do that here. Yeah. Okay. And then you don't have to.
If you're on the DMS network.
I'm not, but I have Wi-Fi hotspot. So.
Oh, didn't make it into the.
Yeah, just click that one, that top one there.
Oops. Too late. Okay.
Right.
Okay, we'll stop presenting from this one. Admit. Ray to the meeting. Oh, we're not presenting on this one. Okay. Okay.
Still using the camera.
You,
Yeah.
good for you. There we go. Is that me? Yep. Okay.
Okay.
All right.
All right. Okay. I need to go into present mode. Share. Sorry, an error has occurred. Screen sharing. Please try again. Oh. Okay.
And you want to Ray, sharing the screen.
It's coming up with an error. Can't share your screen. Sorry, an error has occurred when screen sharing. Please try again. I wonder if I should get out and come back in or something.
Huh. Well, maybe. I don't know.
Dismiss. Stop sharing. Okay.
Well, maybe you could say, tell us what you were trying to show, Ray.
Yeah, there's a whole list of examples of things that you can do that the OpenMV can do. So there's, I haven't counted them, maybe close to 100 different examples of all the code that you could, you know, possibly utilize on the camera. So based on just the functionality, the price, you know, I haven't seen any other camera that can do as much for as little money. You know, like this one, okay, you can get an LCD for it, but it's extra. You can also get a Wi-Fi card, but that's extra. You can't really do, you know, very large models on it because it doesn't have enough memory. So it's just kind of a neat thing. This one is actually the second oldest now. There's or second newest rather. There is a newer version. It's got just a slightly larger LCD display. I think everything else seems to be the same. And the printed circuit board is a little different. That actually has a heat spreader in it. There's actually heat sinks on this side of the housing. Let me see if I can. I'm going to get out and get back in and see if.
Tell you what, while you're doing that, I'll just jump in and inject my OAK-D Lite slide because it's. Let's see. Let me share out my screen here. While Ray's getting set up there, and then we can switch back to him, and then we'll call this section of the meeting done, I think, because I think we're losing focus here. Okay, so this is an OAK-D Lite. I can hand it around. It's you'll notice it's got 3 cameras, two stereoscopic cameras on either side, and then a color camera in the middle. It takes about 4.5 watts. The stereoscopic cameras are monochrome. It has the same onboard processing as the PiNSight that Doug showed. So it uses the well, Luxona calls it their Robotics Vision Core, but what it really is an Intel Movidius Myriad X vision processing unit, which has got a bunch of hardware accelerators in it. It's got an image signal processor, 2 neural compute engines, and 16 vector cores. And so its performance goes up to 4 TOPS. It's treated the operation setting for just vision processing, or 1.4 TOPS for AI. Just to give measure of its performance capability. Another setting it will do a YOLO V10 model, about 400 by 400 pixels at 27 frames per second, which is the same spec as DougP. So really, it's like DougP. It's the same thing as the PiNSight that it's got 2 extra cameras for stereo processing, and its selling is depth intelligence for robots. That's really, you know, if you don't want depth intelligence, then you don't need this thing. I've only used it as a depth processing unit. So I had it on my Robotics robot and took a slice across the image that was strategically placed to be the height of the cone, and then put it into the stereoscopic differential dispersion. There's a word in stereoscopy that means comparing the images and looking at the difference between them and deriving it from that. And so I use it kind of like a length scanner of having a stripe where I get certain segments and computed the depth within that segment using stereoscopy. And it actually did pick up a cone sort of semi-reliably, not reliably enough that I actually use it in the competition, but that's been my experience with it.
Have 2 separate higher emitters, just one emitter, one camera.
It doesn't have an emitter at all. It's only 2 monochrome cameras that are used for stereoscopy, and one color camera in the middle.
Right.
The dev environment is like I said before, you declare a processing pipeline, and there are lots of examples on Sonos' website where that you declare all the modules, a library of modules that do filtering and all kinds of OpenCV kinds of functions, and you can string them all together via definitions that you can put in your Python code that then load that definition up into the camera, or you can load an AI model somehow. I haven't done that, and then it screens answers back out into your push computer, be it Raspberry Pi or PC. So it's going to I'm new and it costs 150. So like I said, more expensive. If you want it, it's a good way to go. The performance is at least on paper, pretty spectacular because it's a high-powered vision processing agent, DPU, whatever you want to call it. So that's all I have on OAK-D Lite. Any questions on OAK-D Lite? Okay. Is there anything else you want to say about the MaixCam?
Yeah, it's just that pretty much. Well, I think I said it before that pretty much all the functionality in an OpenMV you can do in this part. And I was going to try to show you like the find blobs routine. You know, you can use that camera to do that. Either way, but I was going to try to get it up. I'm not certain if I can share.
Slide. I did add a slide to it. You did? Oh, let me go find it. I did. It looked to me like it has an ASIC. Sometimes you can process ASIC because it pulls out. It's got an SG2.2 GPU. Am I right on that, Tom?
Sorry, your audio is all broken up, Paul.
On that,
Okay.
the documentation isn't real great.
Okay.
But yes, I'm saying that like one tops. So
yeah.
Yeah, right. If you see something that is working in TOPS, teraflops, you pretty much have to can assume it's got an ASIC in it because, 400 megahertz processor can do a billion floating point operations or face any kind of operations a second.
No.
Tera, that's 1,000 billion.
Teraflops, yeah.
Yeah. A CPU just can't do that level of clock. So if it claims clocks, it's pretty much got an ASIC in it. Okay.
Okay, so I did add a slide to the thing. I don't know if you got it. You can put it in there.
Oh yeah.
Yeah. You guys want to get this? I think this would be of interest to people. This is pretty much just.
Okay, sure.
Okay. Okay, so this is the Raspberry Pi AI kit. Okay, the actual it comes as a hack. It conforms completely to Raspberry Pi plus specification, and it's made so that it comes with hardware that allows you to lift it up a little bit so that you can have the active cooler in place. There are 3 versions. There was the original kit they came out with called Raspberry Pi AI kit, which actually came on a PCI M2 board pack, and it's a little module that fits into that. Okay, and then they came out with 2 new modules where the Halo-8 or AL is actually physically soldered on to the hat. So it's not on the first one that came out, you can take the module out. And I guess if you had another computer or something, you could use it on it. Okay. It uses any live camera or even a webcam. It just uses a video stream basically. And the interface is PCI 3. They have 2 versions. They have the AL, which is the 13 top, and the 8 has 26 tops. Okay. What I'm demoing is an AL, and it has a. If you look at it, it has the yellow ES model frame rate of about 49.5 frames per second. Using their benchmark ResNet 50 model, it actually has 500 frames. I don't know. I've never found that model, and I don't know what it can do. I think it's the benchmark. The development environment tailored software, which is where the rub is at, because I haven't seen an unbugged version of it yet. People have got it to work, but there's a lot of people who haven't got it to work. So I think there's a little more learning. This company is out of Israel. What I did was I used the Colab hosted Jupyter notebook to run a model, generate an OMS file. And then I got to the point where you have to use their compiler to turn the .OMS file into a .ATF file. That's where I ran into the issue. I had the compiler telling me I had to have 2 versions of NewBie, and they were different and they were mutually exclusive, and so that didn't work. But I want to point out then that if you're trying to learn all this stuff, there was a set of 4 articles, but it's been issued by Cytron. That's absolutely very good. And that's the starting of the 4 articles. They change from there. Okay. Okay. Right. This is another thing. Like I say, when they first came out, Raspberry Pi said it was going to be $70. So the list price is $70. All right. Right now, if you guys do the Check Micro Center, they probably have some of both of the Halo 8L stuff in stock at that price. If you go to Cyclone, which is out of England, I believe, it's $77, but they got a special. Now, if you want to go to the 8, that's the 23 cost version. They have it would be $110 at Micro Center, but they don't have any. So it could be $50 a year. But that's what if they had them, that's what they would sell them for. Now, from Cyclone, they're 136, and there's some reasonable stock there. I think there's like 26 or something like that. Okay, now all versions of these kits are being scalped currently at incredible numbers. I might have to be seeing an 8L for $265. So I'm saying, if you want one, go to Microsoft, or you can do it. You can order it online and then come pick it up in the next 3 days. It's not something you have to do. But now, if it's new 29.5 frames per second with the VA, the vote, the VA, mom, I'm not upset about my purchase of the 13. Okay, if I were to get it today, I might get the 26 because the difference between 70 and 136 isn't horrible. You know what I mean? Now, we're trying to maybe.
Do you know which ASIC it uses, Doug?
There's a lot of stuff that's behind the curtain.
All right.
If perhaps I could interrupt for a second. There's three mics in the room.
What it looks like.
The sound a lot. Perhaps we could just have one mic.
See here, how do I pin myself? Okay.
For everyone.
It's not showing. That's right.
Okay.
All right. I don't know. It doesn't look like it's showing on the screen, but can you guys see me?
We can stop sharing.
Okay, we have 1, 2.
Yep, we got you pinned.
Okay, now I'm going to switch cameras.
Okay.
All right, now here you can see it's using, like I say, I think it's some form of, well, YOLO, but it's probably using the mobile whatever data set that has 30 different items. And you can see here it's picking a laptop and people and a chair and a bunch of other stuff. Let me set the camera up right. I can. Okay. All right. So I'm just using a version 2 camera, and this one's probably not the best because it's got a wide field of view, and you can see that if you look at the picture, there's a little bit of a corner rounding. But here's what it is. So here's the hat. It slides over your GPIO bus. If you want to use your GPIO bus, you have to buy some sort of little extender here so that your GPIO bus pins will stick up above. Okay? And I'm using a DSi monitor on that. That's why everything's kind of cramped. But so here's the module right here, and it's being joined into the hat. You can see that it's tied to the PCI bus right here. So if this matures a little bit, I think this is at $70. I think this kind of kills everybody. So I don't know.
Interesting.
Something to think about. Okay.
So that is relevant to this smart camera discussion from the perspective of it's a smart without the camera.
Yeah.
But yeah, so it's interesting.
Yeah. I think, you can do something like this with an Intel neural stick.
Right.
You
Yes.
can do the same. You can plug it into one of the USB ports.
Yes.
And do something similar.
Yes.
Just not at
Right.
speeds that they're talking about.
Right. And the newer Intel neural stick uses the Myriad X.
Yeah.
Movidius Myriad X ASIC.
Right.
And this uses, I guess, their own ASIC.
Yeah. So anyway, I thought since we were having this panel, I thought people would find it interesting.
I think this is right on. It's great information. Thank you, Doug.
Right.
So I guess it's probably time to wind this up. We've kept these poor people trapped for 4.5 hours now. But I think it's worth just wrapping up with going back to David's question. If I was buying a camera today, what should I buy? And to some extent, it maybe depends on what you want to do. If you need depth, I'd say, and you got 150, I'd say it's not a bad choice to go with the OAK-D Lite. If you don't need depth, then what Doug said about the PiNSight could be good. Ray's MaixCam also seems good for a pretty good amount of power for not much money. Seems like Tom's ESP32 cam is probably a little lower end than you want for a robot.
I think that would be great for a job like monitoring a mailbox.
Yeah.
That's something like that.
Yeah.
I think, or would be really good for that.
Yeah.
I guess, if maybe I'm biased, but if you want ease of use, I would probably go with the PiNSight or the OAK-D Lite. Okay, depending on what you want.
Mm-hmm.
Depth is intriguing, and if you've never played with it, it's fun to play with. But there's some new depth only cameras that might be a more fun alternative to get your feet wet. Now, doing serious work, I'm not sure they're as good at that, but to just play with depth and try to figure out how it used, there's the MaxiSense A101, I think is worth playing with.
Yeah, which Ray has used, and
Pat's got one as well.
Yeah, Pat's got one of those. A010. Yeah.
So
that's pretty much just a depth camera.
it's getting kind of hot in here, and the energy level is kind of sagging. I think it's probably getting to be time we wrap this up. But does anyone want to have any? Should we open the door and
Let people escape.
Yeah. We don't usually run over this badly. I think it was a really interesting panel. And, a lot of interesting information. So thank you to the panelists who gathered all that information. Any closing comments, questions? Okay, so I think what we should do at this point is declare the formal part of the meeting closed, open the door so we can let some cool air in or cool air out, whatever, whichever way that wants to go. And then if people have show and tells that people are interested in, like Mark's got a show and tell, then feel free to hang around as long as you want. We've got this room till we don't want to be here anymore. Yeah. But let's call it, you don't need to feel embarrassed about walking out at this point. Cool. Well, thank you everyone for coming to the meeting. I'm sorry it ran long. We don't usually run long like this, but we had a lot of stuff to cover. So thank you for coming, and see you all in next month.
You muted, Tom.
And on Tuesday.
and at RBNV, if you come to RBNV on Tuesday, and we'll come up with some set of how we. I mean, there was a great discussion on what do we want to do this year, and so I feel interested in some of the things that came out of that discussion. So I'm keen to see if we can make some of that real.
Yeah. Cool.
All right. Thanks, everyone.
I was going to do a quick demo on algorithms. I know that